What is happening, everybody? Welcome to another MLOps community meetup. And today we had a first time thing happen. That is, our scheduled guest ended up being a little bit mixed up with the times because they just moved to a new city. And so they got stuck in traffic and had to bail on us. But luckily enough, I was on a call with our new guest, Blaise, and he said, "Oh, yeah, I got a talk that I could do." And the rest is history. Now we are going to do something that is a little bit different than what you probably signed up for, but hopefully it's just as valuable and just as interesting. So I want to introduce our guest of honor, Blaise, with a song like usual. And before I go anywhere, so that everyone knows what we're going to be talking about today, we're going to be doing a talk on from the intractable to intertractable, unleashing sensitive data sets with distributed data science. All right. So Blaise is an incredible human. Let me just give his intro for everyone. I've got Ben here with me too in the background. I'm going to bring Ben on real fast just to make sure that I am. Oh, sorry, Ben. I just kicked you off.
That's okay.
What's up, dude?
I'm doing great. I'm actually really excited for this talk. How are you?
All right. So, can you hear the guitar?
Always.
All right. You hear some noise. That's what I like. Oh. No, that's too sad, huh? I think we gotta make it more interesting. Cause Blaise Thomson is the founder and CEO of Bitfount, a federated machine learning and analytics platform. Oh, well, before that, he was the founder and CEO of Vocal IQ, which sold to Apple in 2015. Subsequently, leading their Cambridge, UK engineering office and holding the role of chief architect for Siri understanding. Blaise holds a PhD in computer science from the University of Cambridge, where he also was a research fellow and is an honorary fellow at the Cambridge Judge Business School. He's coming on to give us a little sneak peek into what they're doing at Bitfount. I'm so excited to have you here, Blaise. Let's bring you onto the stage. Welcome, my man.
Thank you. Very unorthodox, but exciting. I like the sound.
It's great that this happened. It's great that this happened actually now, because for all those people who have been commenting that Demetrius is spending hours planning those songs before people come on, that literally could not have happened this time.
No.
Yeah, 10 minutes maybe max. But it seems
Yep,
like
that was fully improvised. That was can't get more improvised than that. And so oh I just got somebody jumping in right now that is asking in the chat. Ronan, you wanted to know about creative AI event. the speaker for that event just canceled on us last minute, so we switched out with Blaise, and Blaise is going to talk to us about all this cool stuff. Blaise, I see you're sharing your screen, so I'm going to kind of hand it over to you right away, and I'll let you get rolling, man. Thanks
Okay.
again for pinch hitting and jumping in last minute. Think people are still going to enjoy this just as much as they would have the other one. So let's get after it.
Yeah, thank you very much. And I apologize to everyone already if you are looking forward to creative AI, which is a very cool topic. So I hope this can be equally interesting, if even though it's quite different. So I'm talking about working with sensitive data in this talk. And so sometimes we talk about changing intractable data to interactable. Um, and we'll go through some of those things as I go through the talk, hopefully. Um, so yeah, interactable, because with this kind of data, you can't necessarily always directly see it, but you still want to be able to do analyses on top of it. And that's kind of this idea of distributed data science. You might have also heard of federated learning, privacy enhancing technologies, a whole bunch of things like that. So yeah, this becomes really interesting and useful when you're dealing with data that you wouldn't be able to access otherwise. So maybe stuff like medical data, financial data. In big tech companies like Apple, Google, this often gets used to do things like training on device using data that you wouldn't be able to send back to the servers. So, for example, Apple and Google as well want to train on the messages that you have in your phone, but obviously would get into a lot of trouble and don't really want to anyway transfer those messages back to their servers. So I'm going to try and give you a bit of an introduction. There's some quite cool technologies which can be used, and then talk about some different ideas: usage-based access control, privacy techniques, and some examples. So hopefully it'll be fun, although admittedly very much less visual than some cool creative AI. Okay, so the premise here is like, basically, as you know, you can really transform the world with data, but actually quite a lot of this data is getting more and more regulated and protected. So there's like a whole ton of legislation coming in about what happens to data and making sure that it's done in an ethical way. People getting into huge amounts of trouble because of data breaches. They can either lose tons of money, or they could also sometimes just have a lot of reputational damage. And so this is kind of leading to a whole lot of problems. And I think what's basically going wrong is that a whole bunch of things. So the release data, when you work with someone else, that data could be really private. And if it's personal data, then it can cause problems once it's released. A lot of what people are doing are mostly about what data is used. So the controls are often about like who has access to what data, but actually what people really care about with their data is how it's being used. And so we don't really have a good way of managing that. And also there's just like, sometimes it's too much data. You kind of want data control, at least, to be a bit more federated. And so you might have heard of this push towards data meshes, and that's one aspect of that that people like ThoughtWorks and so on are pushing for. But underlying all of it, I think, is this thing that once data is transferred, it's not really under your control anymore. And so that can cause a lot of issues for companies. And so if you're thinking of like a data ops pipeline, so maybe a bit less MLOps, you can get into trouble basically because you've transferred the data out and then you're not really sure what's going to happen to it. So in distributed data science or federated machine learning, the basic idea is that instead of sending data to where you do the analysis, to where the algorithm is, you send the algorithms to the data. So it's quite a simple idea, but actually has quite big impact in lots of different ways. So just to kind of make this visual a bit more, you basically got a data scientist that's got some task in mind. They send it through some orchestration platform. That's kind of what Bitfount is, our company. It gets to the relevant places where you want to do the compute. Those places can add various privacy protections before any data is sent back. And they can also check whether this data scientist has permission based on usage. So that's quite a different access control model than the normal one, which is based only on the data. So now instead of like this concern where you're not tracking what data is being used, now you can actually have these usage-based controls. If you're worried about the data being private, well, you can have privacy protection before you share any data, because you're always sharing the results of various analytics. And you can also federate the governance if you want to do that. So just again, to reiterate what I've basically said already, normally you would say, okay, who has access to what data? But now you're saying also who has access to what data and how are they allowed to use it. And so that's quite a fundamentally different facet, if you like, of access control. So the question, of course, is like, well, what kinds of permissions would you have? Kind of thing you might want to say is like, well, this person, they're allowed to evaluate machine learning models, but they're not allowed to train a machine learning model. And that comes up for us. We're doing some work in clinical trial recruitment, and there you've got a pharma company that has a machine learning model, and they just want to evaluate it in a hospital, and that will identify the patients for a trial. But they, like the clinic is happy for them to send their model to be evaluated, but they don't want any data leaving. Another thing you might be willing to do is allow people to train a machine learning model, but not actually get the data. That's the kind of thing that Apple and Google do on their phones. But actually, you also have that in various situations where you've got collaborations between organizations. And then you might be willing to allow people kind of arbitrary queries as long as private data is not kind of reproducible. And there are some techniques, which I'll talk a bit about. For example, differential privacy, which gives some protection about how much data can be shared back. Okay, so let's just quickly talk about some quite cool privacy protections that people have been working on. And I think it's quite useful to think of these in some different categories. So if you've got some raw data and it's kind of going through various phases to get to someone who wants an insight, there are a few things that you can do. So one is I kind of call the category of data modification. So you, for example, can tokenize a whole lot of the data. So you replace anything that's personal with a token. So any first name that comes up, you just replace it with first name token. Same with surname, maybe same with phone numbers, same with credit card numbers, and so on. And so that kind of obfuscates a whole bunch of the data, and that can lead to something that people consider to be reasonably anonymized. Of course, you do potentially lose some information there, and then you can do hashing, but that can also be attacked. So there are some potential issues around the tokenization. Synthetic data is something people have looked into as well. So you can just code up something that kind of roughly reproduces the statistics, and that can be quite useful for testing. I think there are attempts to do this in a more kind of machine learning type of way using GANs, and that's quite popular, but also can have some potential problems. And in some cases, unless differential privacy is used, can also be used to reproduce the data. Then you could just share aggregations. So you might say like, oh, I'm happy for people to know sums or averages, things like that. You can randomly add noise to the data, and that's essentially what differential privacy is. And that can kind of obfuscate as well. So there are lots of things you can do to data. Before you let it out of your control, you might have a whole bunch of different types of disclosure control. So historically, a lot of people have just had human checks where they look at the data and try to make sure that they feel like it's anonymized enough. There's a concept that's quite popular called k-anonymity, which basically says as long as you're sharing aggregations which have at least k entries, then it's okay to share. So for example, if you have a sum which has 10 values in it included, then that's kind of fine to share. The problem, of course, with that is that if you allow 2 of those k-anonymous queries, you can often reproduce anything, because you can calculate a sum which has 10 entries and then a sum which has 11, and you know that 10 of them are the same, and then you can calculate the one. Yeah, and then differential privacy is this idea where you kind of randomly add a bit of noise, and that gives a quite nice concept of privacy. If you're doing collaborations, there's another type of set of privacy technologies which have become quite popular. And those are to do with confidential collaboration. And essentially what they allow you to do is calculate overall aggregated functions without knowing the individual values. And there are 3 main ways, I think, of doing this. One is called a trusted execution environment, and that's a special kind of chip from Intel, or actually various of them. There's also an AWS approach. There's Apple has some approaches, but Intel's probably the most well-known of these, called the Intel SGX. And it has some hardware protections to try and make sure that no one would be able to see inside of the chip. But at the same time, you'll know what the output computation would be without necessarily knowing the inputs. Homomorphic encryption is an encryption-based way of doing a similar thing. And secure multi-body computation is an approach based on network protocols, which again kind of does the same thing. So that's kind of high-level overview of a whole bunch of different privacy technologies. So now I think it'll be quite fun to just look at some examples of this, because it's quite surprising actually when you realize how simple some of these things are. So a classic example here is you've got someone who wants to know what A plus B is, where A and B are held by 2 other parties, and no one wants this person, the data scientist, to know what A or B is. So what A and B do is they just exchange a random number X, and A sends over A plus X, B sends over B minus X, and then they end up with a sum without knowing because they don't know what X was, they can't work out what A or B was. But because the X's cancel, they get A plus B. And so it's really super simple, and you can generalize this to do essentially arbitrary computations, but it gets more and more computationally or network intensive to do more complex computations. So that's one super simple version of it. And this already gives you quite a nice technique when you're doing machine learning, because if you want to train across data in multiple different sites where they all have the same schema, you would anyway be doing stochastic gradient descent. And so you can calculate the gradient across all of these different sites using secure aggregation, so that you can end up with a kind of aggregate gradient without knowing any of the individual ones. And so that's quite nice, because you then don't know which of the participants contributed their gradient. You can also add differential privacy if you want to add extra privacy protection. So just an example of this in action. This is an example data set from Kaggle, where you're trying to predict eye disease from these images. They're OCT images, and there are 3 diseases. One's called drusen, CNV, DME. And here we just did an experiment where we split them into different sets of data with different distributions of the disease. One which has mostly drusen, one which has mostly DME, mostly CNV. And then, as you'd kind of expect, if you train on the data set that has mostly drusen, and then you test on that same data set, you get a pretty good accuracy, and better than if you trained on mostly DME, mostly CNV, and so on. And similarly, you can see this kind of diagonal gets the best accuracies. But if you're able to federated train across all 3 data sets, just because you're seeing more examples of these images, you end up getting quite nice improvements in accuracy or reductions in error. And so actually in this case, the best model is one that's trained on everything in all cases. So it's better than any of the other models. And so that's, I guess, just one example. It's maybe not that unexpected because you're basically just training on more data. But what's quite important here is that this technique allows you to train on data that you might not have otherwise been able to access. So that's federated learning. Another quite fun example of doing this confidential collaboration is private set intersection. And so in this use case, you've got two sets of entities. So here, for example, you've got some names that overlap, but some that don't. And so you might think of this as like an example where you've got a customer list in your company and you want to check how much overlap it has with the customer list in another company. This technique is actually also used for identifying whether passwords have been reused, or actually whether passports have been hacked. So there's like a list of passwords that have been hacked, and then you can check whether it's whether one of your passwords is in that list without sharing what your password is. So there's lots of reasons you might want to use this for data resellers, for federated learning, so that you can do a different kind of federated learning, actually, where you want to try and link up data sets, maybe for investment banking and so on. So how does this work? Well, the naive way, of course, is you just hash everything, and then you send over the hashes, and then you check if the hashed values match. And that works okay, except that quite often you can do a dictionary attack, so where you just try every available option. So certainly if you have names, for example, it's quite easy to just try out all the names and eventually find the ones that match, because you can just, it's quite easy to hash, basically. And so what you can do instead is you do this little protocol where you essentially applying a salt to your hash, but the two sides apply different salts and they work together to eventually get something which has both salts applied. So as long as you have a hashing function where you're able to apply hashes repeatedly, what you can have is A sends over their hashed value with their salt, B sends over their hash value with their salt, and then A and B apply their salt to the hashed value that has come over from the other side. So so here now A would apply their own salt to the thing that they got sent by B, and the same for B. And as long as the exponentiation here is commutative, you can, which means you can switch the order, you can now check whether your hash is matched against the other person's. And so you end up working out what the overlap was without any risk of your secret values being shared. Cool. So that's a very quick intro, I think, to some of these ideas. I'm just going to finish off with a few kind of different use cases, which I think are quite fun. So I guess I think there's kind of four broad sets of use case, depending on whether the people providing data are in the same organization or not, and how many of each of them there are. So if the data scientist and data provider are in the same organization, then you can think of these techniques as essentially just providing internal access controls. But that can be valuable for various reasons. For example, if you want to train across jurisdictions, it can be the case that it's really hard to transfer the data. In the embedded case, which is one where you've kind of got one data scientist or one organization for data science, and then multiple data providers, that can be really interesting when you're trying to leverage data that's in a customer's data silo that they wouldn't be willing to transfer to you. If you're trying to sell your data, then that can also be really helpful at this kind of idea, because you don't have to transfer your data and people can just test it out without transfer. And then finally, you have some situations where there's kind of a conglomerate or consortium of different people who all want to benefit from some kind of shared data. For example, if you're doing benchmarking or training across shared data sets. And so I quite like this set of different configurations to think about the different cases. So just going into each one, the internal ones, you've got some kind of data mesh ideas to distribute ownership or governance of who has access to the data. Sometimes if you have really large remote data sets, you don't want to transfer them. And so this can be a way to still leverage those data sets and kind of maybe also if you have like a multi-cloud type setting. If you have these big group companies, then sometimes it's not really possible to transfer the data, but you still want to leverage them. That could be just because of the organizational boundary, but it can also just be that you're, for example, working with data in China or even between Europe and America. It can be pretty hard. So that's a reason to use these kinds of techniques. Training on customers' data can be quite an interesting one, especially if you have a more kind of ML AI type company, and if your whole product is about building AI models, then often you're selling those models to customers, but they don't want their data to be transferred out of their cloud, or at least they might want it to be stored in a separate AWS organization or similar. And so this means that you can start training across those. Similar ideas if you're working with suppliers, you might want to leverage their data. Then there's data resellers. You might, like if you're selling data, then you might want to work out the overlaps with potential customers, but you don't really want to transfer your data. Another thing you might want to do is have people test out your data without actually having to sell it or transfer it over. And that could be pretty interesting. And then selling data access instead of data itself. I think that's not really a very common business model, but you could imagine evolving that for cases where you want to keep hold of the data. And then finally, the alliance type use cases where you've got a whole bunch of different people collaborating, maybe for research, maybe for benchmarking, these kinds of use cases. Okay, so to summarize here, I guess the whole idea of this whole paradigm is you don't always have to send data to where the algorithm is. There are methods where you can send algorithms to the data, and that enables you to have various privacy protections, some usage-based access controls, and federated governance. So that's a quick introduction. If you want to try out some of these ideas, we actually we launched this open beta, so it's free to try. You can play around with the tutorials, sign up. We have a community forum and so on. But yeah, I'd love to hear thoughts or questions, and hopefully you weren't too flummoxed by the change from creative AI to more.
I think this is pretty creative in and of itself.
Yeah,
this is human creativity, though.
Yeah, absolutely.
Yeah. So I actually have a couple questions on this. So if I'm understanding your talk kind of correctly, the idea is that in many ways you can keep encrypted data encrypted or obfuscated data obfuscated as you're training models. If you're in the space where you're training models and maybe those models are trained, you put them into production and they're not performing as well as you'd want them to perform, how would you then go about analyzing mistakes, understanding your data errors, and finding kind of interesting cohorts if you don't have that obfuscation kind of mirror?
Yeah, it's quite challenging to. It is quite a different type of approach, I think, when you don't get to look directly at the data. So we do things like you can still do kind of SQL type analysis, where you still try to get histograms, for example. You still try to get a sense of how the data is looking. But the problem and the challenge, if you like, is that you don't get to actually see the specific data. You can also test out the data, like test out the models that you're training on your own test data, which you can see. So I think you can still see some of the artifacts coming through if there are any. So I think you do want to have some of that that benefit. But yeah, it's a challenge. But at the same, I guess it's just a bit of a trade-off. It's like, is the benefit of the extra data worth it for the fact that you weren't able to see that extra data? Yeah, and I guess it sort of comes down to the particular use case. You know, is that worthwhile?
Are you guys? Well, I guess I have two follow-ups. That one, you said something like printing out histograms with SQL queries and things like that. Is it mostly work based on structured data, or do these techniques also apply to unstructured data?
Yeah, it works on both. We've done, in Bitfount we've done tabular and we've done image-based models. In Apple, we did some stuff with NLP type models as well. So you can do NLP as well. Yeah.
That's awesome. And as maybe I should have asked this one first as a follow-up to your response, are there things that you guys are working on in terms of like implicit bias detection or kind of I don't know, model failures as such? Kind of the model might be training, but there might be ways to detect based on like the embeddings or something like that the model's actually not learning the way that it should, even without seeing the data.
Yeah, we haven't done a lot on that, to be honest. But I think some of the same techniques that you might use in like normal machine learning will apply. Because fundamentally, you're basically doing the same thing. It's still a distributed data set, distributed gradient descent. And actually, in like big models, you do it distributed anyway. It's just that it's more distributed now.
Right.
So it's like the training paradigm, if you like, it's not really that different. Except that, well, sometimes there's a bit of a trade-off because of the network overhead of transferring the model weights around. So sometimes in federated learning, you'll start leaving it to train a little bit longer remotely before sharing the gradients back. So you would do several batches remotely and then average the model weights rather than kind of calculating the immediate grade, so like doing the whole batch at the same time and then doing the iteration. So there's a little bit of a different calculus there in terms of getting, like, essentially in terms of your hyperparameter optimization.
And are you not doing this because it's something that only occurs or it happens in theory, but you don't actually find it that much in the field? Or is it just because you haven't gotten there yet?
Yeah, I think it's, I guess it's probably both. Well, at least like so far we haven't had it come up as like a major issue. And actually, federated learning can even be used as a way to solve for bias because, well, it depends on the kind of bias. But if your problem is that you aren't able to get enough data of a particular demographic, for example, then federated learning can actually help you because you can then start getting more examples. And so we actually have a project going where we're exploring that with medical data because you basically, like, different hospitals will see different demographics depending on the area that they're based. And so you kind of want to get a collection of different hospitals in order to be able to get a better set of demographics. In terms of bias detection, I think, again, it depends on the method, but you can basically run a lot of the same methods to try and work out what's happening there. Yeah, but it's something we're really starting on now on the bias side.
Mhm.
That's really
So there's a question that came through in the chat from Anders, and they're asking, have you come across any open source frameworks that help with these approaches for those who want to skip the details? Just the shortcut. I feel you, Anders. I feel you.
Yeah, well, so we're basically providing one. So you can try.
Nice. There you go.
But probably the biggest community is around a tool called PySyft. So you can try that one as well. I guess the reason we try to do a different one is we thought we could make it a lot easier. And that technique, I guess a lot of the architecture is built around an assumption where you can set up a incoming internet connection, which what turns out to be a bit problematic for enterprise customers or the people that we thought would often want to use this thing. NVIDIA also has one that's also, I think, quite challenging to set up. I think, yeah, I basically recommend people just try a few of them, but ours is certainly free, and the client library for sure is open source.
Nice. Nice. I just threw the link in there into the chat for Bitfount, and then also I think the PySyft is from OpenMined, right?
Yeah.
Yep. So I threw a link to that in there too. Dude, this is super cool. I know that you don't have that much more time. And so I want to finish with maybe a question that is not related to the talk that you just gave, but I think people would enjoy hearing. When it comes to your time at Apple, is there anything you can tell us? Like, did you ever have any huge ML oops or war stories that you can divulge? And we can cut this out of the recording if you sign some NDAs or anything.
MLOops. I mean, I think Apple has a quite amazing ML infrastructure, so I think that's like not a secret. MLOops, like I guess I wouldn't say it was an oops, but like it wasn't so clear to me until like working much more in industry how much you can get from not ML, if you like. And so like a lot of the things that are challenging in a normal, like in a company that's delivering a product, is like people want certain things to just work all the time. And so I guess it took me a while to adjust my thinking to like not always have to do everything with machine learning, to also leveraging things that, for example, if someone says "cool mom," like it doesn't really matter what the machine learning model says. We kind of know what that means. Yeah.
Wait, can I interject in there for a moment, because I do use Siri to say like FaceTime mom, and occasionally it'll pop up because I have from when I used to teach English years ago. I have like Anders' mom, his name, or Jason's mom, because they were my English students, right? And Siri will pop up like, which mom do you want me to call? I'm like, I don't want to talk to these people's moms from like 8 years ago. And so that does kill me. And I know it's not your fault, but if you still have some friends that work on the Siri product, maybe a little bit of non-ML to fix that problem would be amazing.
I have seen some projects in that space where it's like doing ML, but with regex. Like you can accomplish 50% of what you want to do just with really good regex.
Yeah. But the problem with that is that then it's quite hard to switch back to machine learning. So I think, and because it's like quite hard to identify the things that are not working with the regex, I think, yeah, but that does get you going, right? Yeah.
It's possibly the case that regex is harder than machine learning in some cases.
Yeah, absolutely.
Yeah. And totally random on this regex point, I just saw yesterday some foundational models being used to take English and translate it into regex. I'll try and share a link to that in a minute.
That's really cool.
Yeah, I thought it was hilarious.
I would pay for Copilot if it did that for me, for sure.
There we go.